Hello everybody. Right now, 95% of the universe is invisible to you, and yet, it's what holds galaxies together and drives the cosmos apart. You can't see it, you can't touch it, but it's everywhere. When we gaze up at the stars, we're mesmerized by the beauty of galaxies, nebulae, and distant supernovae. But what if we told you that everything you see, stars, planets, dust, gas only makes up 5% of the universe? The other 95%, it's something far stranger. Scientists call them dark matter and dark energy, not because they're spooky, but because we still don't fully understand what they are. They don't emit light, they don't absorb it, and they don't interact electromagnetically. Yet, their gravitational effects shape the entire cosmos over the last few decades. Astronomers and physicists have uncovered clues hinting at their existence. Galaxies spinning too fast, defying Newton's laws. Massive galaxy clusters bending light in ways that require invisible mass. And perhaps most shocking of all, the accelerating expansion of the universe. In this video today, we dive into these two cosmic phantoms. What is dark matter really made of? Is dark energy a force, a field, or a flaw in our understanding of gravity? How are scientists trying to detect the undetectable? Join us as we explore the greatest mystery in modern cosmology and ask, how much do we truly know about the universe we live in? For centuries, when we looked up at the night sky, we believed that what we saw, stars, planets, nebulae, was all there was. But in the 20th century, everything changed. Scientists began to notice something strange. The visible matter in galaxies did not account for their actual mass. In fact, galaxies were spinning at speeds that should have torn them apart unless there was something invisible holding them together. That invisible something was given a name: dark matter. But what exactly is dark matter? The truth is, we still don't know. It doesn't emit light. It doesn't absorb it either. It doesn't reflect, refract, or scatter electromagnetic waves. It is completely invisible to every form of light and radiation we've ever invented tools to detect. The only reason we know it's there is because of its gravitational influence. One of the most striking examples comes from Vera Rubin's research in the 1970s. She studied the rotation curves of galaxies and found that stars far from the galactic center were moving at the same speed as those near the core. This defied Newtonian physics. According to the laws of gravity, the outer stars should have been moving slower. The only explanation: a vast halo of invisible matter surrounding the galaxy, exerting gravitational pull, dark matter. Since then, scientists have searched for ways to detect it directly. They've built underground detectors, sent particles smashing into each other at near light speed, and observed distant galaxy clusters to try to learn more. But so far, no direct detection has worked. There are many theories. Some suggest dark matter is made of exotic particles that rarely interact with normal matter, called WMPs, or weakly interacting massive particles. Others propose axions, sterile neutrinos, or even modifications to our understanding of gravity itself. But no matter the theory, the effects are undeniable. Without dark matter, galaxies wouldn't form and hold together. The cosmic web of structure across the universe, galaxies connected in a vast, intricate network, would not exist. Dark matter shapes the universe on the grandest scales. So we know it's real. We know it's essential. But we still don't know what it is. And that mystery, the cosmic question mark, continues to drive some of the most exciting research in modern physics and cosmology. You might be wondering, if dark matter is invisible and we've never directly detected it, how can we be so sure it exists? The answer lies in the overwhelming weight of indirect evidence, clear, consistent, and impossible to ignore. The first line of evidence comes from galactic rotation curves, as we discussed with Vera Rubin's work. In a galaxy, the farther you are from the center, the weaker the gravitational pull should be, and so stars should orbit more slowly. But that's not what we observe. In spiral galaxies across the universe, stars far from the center are orbiting just as fast as those near the middle. It's as if a massive, invisible halo is boosting gravity across the entire galaxy. But galaxies are just the beginning. Look at galaxy clusters, groups of hundreds or even thousands of galaxies bound together. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster and found that the galaxies were moving far too fast to be held together by the visible matter alone. He called the missing mass Dunkel Materie, or dark matter. Nearly a century later, his bold claim is now one of the cornerstones of modern cosmology. Another compelling piece of the puzzle is gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the space around them, curving the path of light. When we observe distant galaxies behind clusters of dark matter, we see their light distorted, warped into arcs or even multiple images. These distortions don't match what visible matter alone can account for, only if we add a massive invisible mass dark matter does the math work. Perhaps the most dramatic evidence comes from cosmic collisions, such as the famous Bullet cluster. In this event, two galaxy clusters collided, and we observed something extraordinary: the hot gas from the collision, which contains most of the visible mass, lagged behind, while the gravitational effects map using lensing moved ahead. This shows that whatever is causing the bulk of gravity isn't interacting with normal matter in the way ordinary particles do. It passed through almost unaffected, just like we expect dark matter to behave. And then there's the cosmic microwave background, the afterglow of the Big Bang. Its tiny fluctuations tell us how matter was distributed in the early universe. When we analyze those patterns, they reveal a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Without dark matter, the early universe's structure would look completely different. These lines of evidence, from galaxies to clusters to cosmic radiation, converge on a single truth. Something invisible and massive is shaping the cosmos. We call it dark matter. And yet, despite this mountain of evidence, we are still chasing its identity. It's like having a shadow that we cannot touch, a force we cannot see, but one that binds the universe together. Now that we know dark matter exists, felt through its gravitational pull, but never seen directly, the next great mystery is, what is it actually made of? Over the decades, scientists have proposed a wide range of candidates. Some are elegant, others bizarre, and many are still being tested in labs and supercomputers around the world. The most popular and long-standing theory is that dark matter is made of WMPs, weakly interacting massive particles. These are hypothetical particles that are heavy, like atoms, but interact with normal matter only through gravity and the weak nuclear force. They were born in the early universe and have lingered ever since. The idea is compelling because WMPs could naturally explain why we have the amount of dark matter we observe today. But despite massive efforts, including detectors buried deep underground to shield them from cosmic noise, we haven't found any yet. Then there are axions, another theoretical particle, extremely light and nearly invisible. Axions were originally proposed to solve a problem in quantum physics, but they also happen to be excellent dark matter candidates. If axions exist, they could be passing through us by the trillions every second without us ever noticing. Beyond particles, there are more exotic ideas. Some physicists have proposed that dark matter might not be made of particles at all, but of primordial black holes, formed in the first moments after the Big Bang. These tiny black holes, smaller than an atom, but extremely dense, could be scattered throughout the cosmos, tugging on galaxies with their gravity still. Other models suggest that maybe we've misunderstood gravity itself. In these modified gravity theories, such as modified Newtonian dynamics, the laws of gravity are different on very large scales, and what we think is missing mass is actually just a miscalculation of how gravity works. However, these theories struggle to explain all observations, especially gravitational lensing and the structure of the cosmic web. There are even ideas involving extra dimensions, hidden layers of reality, beyond our familiar three-dimensional world. In some versions of string theory, dark matter could be a shadow of particles in a parallel dimension, influencing our universe through gravity, but invisible to our instruments. Despite the creativity of these theories, one thing is clear: dark matter is not like anything we've encountered before. It doesn't emit, absorb, or reflect light. It doesn't clump together into stars or planets, and yet it sculpts galaxies and binds the universe in its grip. The search continues in underground labs, space telescopes, particle accelerators, and sophisticated simulations. Each experiment peels back another layer, guiding us closer to the answer. We're not just looking for a missing ingredient, we're trying to rewrite the recipe of the universe itself. Imagine rewinding the universe back to when everything was a hot, dense soup of particles right after the Big Bang. No stars, no galaxies, just chaos. Now fast forward just a bit and you'll see something fascinating. Dark matter was already at work, quietly sculpting the skeleton of the cosmos. Even though we can't see it, dark matter played a central role in shaping everything we do see. In the first few 100,000 years after the Big Bang, the universe was like a foggy soup of light and particles, ordinary matter, protons, electrons. Atoms was jostling around a fast clump together into anything meaningful. But dark matter, it didn't interact with light or other particles in the same way. It started to clump earlier. These clumps, called dark matter halos, became the invisible scaffolding of the universe. They pulled ordinary matter into them through gravity, helping to form the first stars, galaxies, and clusters. Without dark matter, those structures would have formed much later, or maybe not at all. We can actually see the fingerprints of this process in the cosmic microwave background, the afterglow of the Big Bang. Slight variations in temperature and density, mapped in detail by missions like WMAP and Planck, show how dark matter created early gravitational wells where matter could gather and cool. Fast forward a few billion years, and these dark matter halos became the anchors of galactic architecture. Every galaxy we see today, including our Milky Way, is thought to be surrounded by a vast, invisible halo of dark matter. It's this hidden mass that keeps the outer stars of galaxies from flying off into space, despite spinning at high speeds. Even larger structures, the massive cosmic web stretching across billions of light years, owe their existence to dark matter. Simulations like the Millennium Simulation and Illustris show how filaments of dark matter created the cosmic highways along which galaxies formed and clustered, leaving behind enormous voids in between. Think of dark matter as the architect of the universe. Ordinary matter is the visible structure, the stars, planets, gas clouds. But dark matter is the invisible framework that holds it all together. It's humbling to realize that everything we've ever seen, every galaxy, every nebula, every sunset on Earth is just the luminous frosting on top of a vast, dark cosmic cake. And yet, for all its influence, dark matter remains one of the greatest mysteries of our time. In the next section, we'll explore an even stranger player in this cosmic story, one that is not holding things together, but tearing them apart: dark energy. While dark matter pulls the universe together, there is something else out there doing the exact opposite, something even stranger. It's not holding galaxies in place, it's pushing them away from each other, faster and faster. This is dark energy. The idea of a repulsive force in the universe sounds like science fiction. But in 1998, independent teams of astronomers made a discovery that shook cosmology to its core. They were observing distant supernovae, exploding stars that act like cosmic mile markers, and expected to find that the expansion of the universe was slowing down over time due to gravity. But the data told a very different story. The expansion wasn't slowing down, it was speeding up. This was a total surprise. Nothing in our understanding of physics at the time predicted it. To explain this, scientists proposed the existence of a new kind of energy, dark energy, something that makes up about 68% of the total energy content of the universe, yet has never been directly observed. So what exactly is dark energy? The honest answer is we don't know. But here's what we do know. Dark energy is uniform. It doesn't clump like matter. It seems to have a constant density even as the universe expands, which means the more the universe grows, the more room there is for dark energy to exert its effect. That's why the expansion is accelerating. Einstein actually introduced something similar over 100 years ago. In his equations of general relativity, he added what he called the cosmological constant, a term that allowed for a static universe. Later, when the universe was discovered to be expanding, he called it his biggest blunder. But today, that very same idea may help explain dark energy. There are other theories, too. Some physicists think dark energy might be a new dynamic field, often referred to as quintessence. Others think we might need to modify the laws of gravity themselves. Maybe Einstein's equations break down at cosmic scales. One of the best sources of evidence for dark energy comes from observing the cosmic microwave background, galaxy surveys, and something called Baryon acoustic oscillations, subtle patterns in the distribution of galaxies, like ripples in the fabric of space. These observations all point toward a universe where dark energy dominates the large-scale dynamics. But here's the strange part. Dark energy isn't just expanding space, it's stretching it faster and faster. If this trend continues, some models predict a possible end scenario called the Big Rip, where galaxies, stars, planets, and even atoms could eventually be torn apart. It's the ultimate cosmic paradox. While dark matter pulls, dark energy pushes. One helps galaxies form, the other threatens to pull them away from each other forever. So far, dark energy remains a ghost in our equations, but its influence is undeniable. It's the quiet force dictating the fate of the cosmos. In the next section, we'll dive into how scientists are trying to hunt down these dark components through massive surveys, particle detectors, space telescopes, and even experiments buried deep underground. Because to solve the mystery of the universe, we must first confront the invisible. Imagine trying to catch a ghost in the middle of a thunderstorm, using nothing but shadows. That's how it feels to search for dark matter and dark energy to invisible giants that dominate our universe, yet leave behind only faint fingerprints. But scientists are not giving up around the world. Thousands of researchers are working with massive machines, space telescopes, deep underground labs, and computer simulations to track down the clues. Let's begin with dark matter. Since it doesn't emit or absorb light, scientists use indirect methods to detect it. One approach is gravitational. When dark matter passes near visible matter, it can bend light from background objects. This effect, called gravitational lensing, allows astronomers to map dark matter's presence by analyzing the distorted light from distant galaxies. Another approach is direct detection. In underground laboratories, such as the Xenon experiment in Italy or Lux Zeppelin LZ in the US, scientists built highly sensitive detectors buried deep beneath the Earth's surface to shield the M from cosmic rays. So far, no confirmed direct detection has been made, but every failed result helps narrow down the possibilities. Then there's indirect detection, which searches for signals that dark matter might produce when it annihilates or decays, such as gamma rays or neutrinos. The Fermi Gamma Ray Space Telescope and the IceCube Neutrino Observatory are two powerful tools in this quest. Now, how do we hunt for dark energy? Something even more elusive. Since dark energy affects the expansion rate of the universe, cosmologists look at the large-scale structure of space itself. One powerful tool is type E as supernovae, which serve as standard candles to measure cosmic distances. It was these exploding stars that first revealed the accelerated expansion in 1998. Then there are galaxy redshift surveys like DESI Dark Energy Spectroscopic Instrument and the Euclid Space Telescope, which map millions of galaxies to understand how the universe's expansion has changed over time. One more powerful probe is the Cosmic Microwave Background (CMB). Satellite missions like WMAP and Planck have measured the CMB with extreme precision, giving us a snapshot of the early universe. By comparing the patterns in the CMB with how structures like galaxies evolved, scientists can estimate the amount of dark energy and how it behaves. There's even the study of baryon acoustic oscillations about frozen sound waves in the early universe, now visible as ripples in the distribution of galaxies. These cosmic yardsticks help measure the expansion history of the universe, providing indirect evidence for dark energy. While we haven't found definitive proof of what dark matter and dark energy are made of, the hunt itself is pushing the boundaries of physics, cosmology, and technology. And perhaps the most exciting part, every time we fail to find something, we're actually learning more about what it is and slowly tightening the net around what it must be. In the final section, we'll explore the biggest question of all. What does this mean for the fate of the universe and our place in it? Now that we know invisible forces like dark energy and dark matter govern the cosmos, it raises a profound and haunting question. What is the ultimate fate of the universe? For most of human history, we assumed the universe would either expand forever or collapse back on itself in a grand reversal called the Big Crunch. But dark energy, this mysterious force accelerating the expansion of space, has thrown all our predictions into chaos. Let's examine the leading possibilities scientists are debating right now. 1. The Big Freeze. The most likely fate if dark energy continues to act as it does now. It will keep stretching the fabric of space at an accelerating pace. Galaxies will drift farther and farther apart. Stars will burn out. New stars won't form. Over trillions of years, the universe will become cold, dark, and quiet. This scenario is known as the Big Freeze or heat death in this version of the future. Even atoms may eventually decay, and black holes will evaporate through Hawking radiation. After unimaginable stretches of time, all that would remain is a thin haze of particles in an almost perfectly empty universe. 2. The Big Crunch, a possible collapse. What if dark energy is not constant, but changes over time? If it were to weaken or reverse, gravity might eventually win the cosmic tug-of-war. Galaxies would stop receding and begin collapsing inward. Stars, planets, and entire galactic clusters would accelerate toward each other, triggering a final implosion of all matter and energy into a dense, hot singularity. This is the Big Crunch, essentially the universe in reverse, ending where it began. Interestingly, some theories even suggest that a new Big Bang could arise from this final state, giving birth to a cyclic universe of eternal expansions and collapses. 3. The Big Rip, a violent, terrifying end. There's an even more dramatic possibility, based on the idea that dark energy isn't constant but grows stronger over time. In this scenario, the expansion of the universe accelerates so rapidly that it eventually overpowers all other forces. Galaxies are torn apart, solar systems disintegrate, even atoms are ripped from within. This doomsday model is called the Big Rip. It would occur if the equation of state of dark energy drops below -1 into a regime called phantom energy. In such a universe, time itself has an expiration date, the most alarming part, depending on the value of dark energy's properties. This could happen in tens of billions or even a few billion years. Which future will happen right now, based on data from missions like Planck, WMAP, and surveys like DESI, the Big Freeze seems the most probable. The universe appears flat in terms of geometry and dominated by dark energy. That behaves like a cosmological constant, but we can't be sure, because we still don't understand what dark energy is. Our predictions remain fuzzy. We're in the strange position of seeing the path, but not the destination. So, where does that leave us? It's easy to feel small when thinking about the fate of the cosmos, but there's a strange kind of beauty in it too. We are the first known species to ask such questions, to look at the stars and wonder how it all began and how it might end. Whether the universe freezes, collapses, or tears itself apart, the fact that we can even imagine these futures is something miraculous. And we still have time, billions of years before any of these endings unfold. Time to explore, to learn, to build, and maybe one day to understand the cosmic code behind it all. In our final section, let's return to Earth and ask, why should any of this matter to you? What does dark matter and dark energy mean for human beings living in the here and now? You might be wondering, after all this talk about invisible forces, expanding space, and the ultimate fate of the universe, what does this have to do with you and me? It's a fair question. After all, we live on one planet, orbiting one star, in one small galaxy. Dark matter doesn't pay your bills. Dark energy won't fix your relationships. So why should any of it matter? The answer lies not just in what we learn from the universe, but in what it reveals about ourselves. One, a deeper sense of perspective, knowing that 95% of the universe is made of stuff we can see or fully understand, is humbling. It reminds us that our knowledge, our pride in technology and science is still just scratching the surface. It breaks the illusion of control, and yet at the same time, it opens the door to awe, curiosity, and wonder. We are not the center of the universe, but we are part of something vast, strange, and beautiful, in a time when many feel disconnected, overwhelmed, or insignificant. This cosmic perspective can reconnect us to something greater, to driving innovation on Earth. The quest to understand dark matter and dark energy doesn't just benefit astrophysicists. It drives innovation across fields. Experiments like CERN's Large Hadron Collider, neutrino detectors in Antarctica, and space telescopes like Euclid and James Webb push the limits of our technology. In doing so, they generate breakthroughs in data processing, quantum computing, particle detection, and material science, just as the Apollo program gave us GPS, new fabrics, and medical imaging. The search for dark energy might one day lead to technologies we can't yet imagine. 3. The human spirit of exploration. Ultimately, the reason we study these mysterious forces is simple: because we want to know. From the first humans who looked up at the stars and mapped the constellations, to today's cosmologists decoding the CMB, we are a species driven by questions. What is the universe made of? Where did we come from? Are we alone? The pursuit of these questions is not just science, it's the story of being human. We build particle detectors in underground mines and launch telescopes beyond the moon, not because we expect easy answers, but because the search itself gives life meaning. It's our version of climbing mountains, crossing oceans, or composing symphonies. It's a kind of defiance against darkness, against ignorance, against the limits of our senses. We look for dark matter not because it shines, but because it shapes everything. We search for dark energy not because it's visible, but because it pulls the future of the universe apart. And in that search, we become something more than just observers. We become participants in the universe's story. For our moment in time, we happen to live at a very special time in cosmic history. Billions of years ago, the universe was too dense and hot for life. Billions of years from now, galaxies will drift so far apart that their light may never reach us. Future civilizations might not even see the same sky we do today. The cosmic clues will be gone. But we are here now. We exist in the thin sliver of time when we can still see the distant galaxies, detect the cosmic microwave background, and trace the fingerprints of dark energy. We are the witnesses, the translators of cosmic memory, and that makes our moment not just lucky, but profoundly precious. In the end, the story of dark matter and dark energy isn't just about galaxies and gravity. It is about the invisible threads that shape everything, from the birth of stars to the expansion of space, from the clustering of galaxies to the ultimate fate of the universe. These forces, though unseen, are everywhere. And maybe that's the most beautiful part, because the universe is whispering a truth we often forget. Not everything important is visible. Just like dark matter holds galaxies together, unseen support holds people together. Just like dark energy drives the expansion of space, unseen dreams push us forward. The cosmos reflects us and we reflect it, what we've explored in. This video is more than just physics. It's a mirror, a reminder that mystery is not a void to be feared but a frontier to be embraced. We don't have all the answers, But the universe is generous to those who keep asking. So if tonight you look up and see the stars, remember this. Behind every point of light is a story of forces unseen and a future still unfolding. And you, simply by watching this, are now part of that story. Thank you for spending this time exploring the universe with me. If you found this video fascinating, help others discover it too. Give it a like if you learned something new. Share your thoughts or questions in the comments. I read every one. And if you love space, science, and the mysteries of the cosmos, don't forget to subscribe to Astronomical Library. There is so much more out there to uncover, and we'll explore it together. Until next time, stay curious and keep looking up.